Cerebrum Private Limited is a team of academicians and experts who are into education field since decades. We are proud to be associated with more than 1,500 institutions across the country. We are into academic consultation, teacher training, student training, communicative English, Vedic mathematics, subject-specific training, content development, and many more. Smart Learning is a service-oriented social initiative from Smart Cerebrum Private Limited, wherein subject-specific experts will be conducting online sessions for the student community at large. Please subscribe to our YouTube channel for constant updates about upcoming sessions and topics. All the sessions will be related to the syllabus and curriculum.
We welcome Dr. Balaji Rao sir and all our viewers for today's session. As this session is for Grade 10 Chemistry Introduction of Periodic Classification of Elements. Please type the queries on our YouTube channel. We will be taking up the queries before the session ends. A very warm welcome to you, sir.
Thank you very much. Very good afternoon, friends. I hope you've had your lunch. Yeah, it's almost 3 o'clock, so quite obvious that you have had your lunch. Let's begin today's discussion with lunch. Let's imagine we go to a restaurant, or I would say better than that, a decent hotel where you have a buffet spread. All of us are familiar with this concept of buffet or buffet, as you want to call it. Now, you know that different varieties of foodstuffs are prepared and kept, in small containers, and you can go and pick your choice. And if you have a sweet tooth like mine, like I have, you would definitely go to the counter where the sweets are kept, and you would avoid going to a place where there is very spicy food available. Now, just imagine that everything was kept in one place. Then it would be difficult for you to trace which is where. So we need some kind of a orderly arrangement. And this is what is established, what is done in any good hotel, where they have this buffet system, wherein which we know that different kinds of, and they're labeled. They're labeled. So and so, this is a sweet, that is a sweet, this is jamun, that is that. And then there are other varieties also. Exactly like this, we are going to take up our study of periodic classification of elements. When you open your textbook, you find the mention of periodicity beginning from somewhere of Dobrina's period. But thanks to the age-old system of education that we are following, it should not make any politically incorrect statements. So I am very guarded in my statement here. Thanks to the system of education that has been practiced in our country for so many years, we have forgotten the contributions of our own Indian geniuses, which have been hidden in the closed wells of history. One name that comes back to mind is that of Maharshi Kanad. Maharshi Kanada lived somewhere between 6th to 2nd BCE, before the Christian era. That is, we are now in 2020. He lived 2000 plus some few hundred years before that. He had studied, of course, he was a philosopher, and he had made a lot of study about nature, and he had divided, in fact, matter into different. I'm not going to write out anything. I want you to listen carefully, note down a few points here and there, and probably this will fire your inquisitiveness, your curiosity, and you might be tempted to know a little more about our contribution. Today we are talking about periodic table, we are talking about Mendeleev's table, we are talking about the modern periodic table. We are talking about all the stuff that is of very, very recent origin. I am taking you back before Christ was born even. Kanada, the great sage, he introduced us to 6 concepts. Concept of dravya. Dravya, he said, is a substance. Guna, quality of the substance. Kramana, motion of any particle or a substance. Samanya, that is universally acceptable. Vishesha, particular to a particular substance. And samavaya, inherence, it is present by itself. Now, these are things that have been unfortunately, conveniently forgotten by our teachers including me. When I say teachers, all of us are teachers, and we have not bothered to inculcate this information into young minds. And that is the reason why we've been facing the so-called brain drain. We are having people who go by a rote system of learning, who keep on mugging up things, puking it on the paper, and then somehow find a job somewhere, or write a couple of entrance examinations, go to the Western countries and settle down there and forget our motherland. And we complain that our country is not going to progress. It's all because of the faulty education system that we have been going through. We are, of course, seeing a change in the pattern. So I'm quite sure that in the days to come, we will have a total revival of our own system of education, which is really the meaning of the word meaning of education was meant to be. All right. Now, I become a little emotional when I talk about these, because we were not given that kind of education. We had to learn a lot of things on our own. But fortunately, you have people who can tell you about the glory of our own culture, our own system of learning, our great Gurukula system. And in fact, it is said that in the passing, since it comes to my mind, I can mention about Nalanda University. That is supposed to be the most ancient of the universities, and it had almost 10,000 students learning at one point of time. So imagine what was the kind of learning and what is it that we had given to the world, and we are now not up to that level according to them. Of course, not according to us. We are inherently intelligent. Please remember, as a race, our country has produced geniuses. Each one of you is a genius. Each one of you is intelligent. Each one of you is extraordinary and is capable of doing wonderful things, provided you decided to do so. All right. So then we come to Kanada. Kanada was the man who first gave us the concept of Anu and Paramanu. If you go back to Vedic literature, if you go back to the Vedas, almost 5,000 years ago, 8,000 years ago, some of them are 10,000 years ago, they were all imbibed. There was no writing. It was just imbibed. They got this information from looking at nature, and they just spontaneously made out statements which were not written and scripted. Please remember, all the Vedas were not written and scripted in a book. They came by word of mouth. We had this fantastic Gurukula system where a student had to sit at the feet of the Guru. Today, we can't expect all that to happen. Anyway, scenario is different. So the teacher would say things, and the Shishya, the student, would imbibe, remember everything and practice whatever was said. This was our ancient system. It reminds me of a small story. It is said that Alexander, when he invaded India, he wanted to take away with him not only the treasures, but more importantly, the wisdom of the knowledge of our country. So it is said that he invaded one particular part of Punjab, today's Punjab, where there was one family of priests who were supposed to have learned all the 4 Vedas by heart. They knew every one of the Vedas word to word by heart. So this man went there. He surrounded the small hut where the family was living, That family incidentally had a husband, wife, and 4 children. And his messenger went to that priest and told him, hand over whatever script you have, whatever the scriptures you have, the script form, give it to us. That man said, no, I can't do it. He said, then we'll have to kill you. He said, okay, give me 24 hours time. I'll give it to you. So the messenger came back to Alexander, and Alexander, I believe, waited. It is said that he was waiting in front of that small hut. The king and emperor sitting in front of a hut with all his army of people. And inside the house, there were a lot of lamps that were lit, and some chanting was going on. The chanting began at some point of time and kept on and on and on the whole night and the next day also, almost the end of the last hour. Then the king could not bear anymore. He barged into that hut. He saw that the priest was throwing whatever he had written on that leaf. All those, remember, you must be knowing this. We didn't have paper, so people used to write it on leaves, the dried leaves of plants. And he put all of them into fire, and he said, yes, emperor, you can take whatever is there in the fire. He said, you can take away whatever is there in that form. Even if you kill me, you cannot take away the knowledge that is stored here. Now, this is the greatness of our people. This is how Vedas survived all these kind of onslaughts for centuries after centuries. Am I emotional? Yes, I have to be. I deserve to be. All right. Now we come to classification as the current, what the trend needs, because all this is not going to fetch you a job tomorrow. This is not going to fetch you a seat in a good, so-called good institution. So we need to concentrate on our curriculum. So on that basis, on that footing, we start with a timeline. I'm going to give you a timeline. I'm not going to write it because the timeline is pretty long. I'll read out the timeline very, very, very slowly. I'll give you pauses in between. You can write the timeline and then begin to realize how the periodic table was really formulated. We begin our journey, the so-called modern classification. It all began in the year 1649. 1649, phosphorus was discovered by a scientist called Henning Brand. He discovered a luminescent material which was shining in the night, and it was called phosphorus, meaning to shine light or something. Then after that, for almost 2 centuries, there was no such activity, no pronounced activity, till 1829, when Johann Dobriner, I think he was a Swedish chemist, he discovered halogens and alkali metal triads. He discovered a triad. We'll be talking about this triad as we go on further. So the point of beginning would be 1649, when phosphorus was discovered. This is where the story really begins. 1829, it was Dobriner who gave us the first concept of periodicity in terms of halogens and alkali metal triads. Then 1862, this again is a man who's not famous, but unfortunately or fortunately, in fact, he was the one who gave us the first proper periodic table. If you look at the current trend of the periodic table, in fact, it resembles what this man gave us. His name was Dishankar. His name is spelled as Dechancourtois. It is not Courteous. It is Dishankar, I think, a quart or something like that. He gave us the first classification of chemical elements in a cylindrical fashion. So if you now today look at the periodic table that is being shown. In addition to the long form, there is also a cylindrical periodic table which you can get to see. He gave us the first so-called proper classification in the form of a cylinder, where he showed that chemical properties of elements are repetitive, in the sense that the elements having similar chemical properties could be kept one below the other. And he showed that there was periodicity in chemical and physical properties of elements. Henry Deschancourt, I don't get his spelling, I'm sorry, pronunciation, I'm sorry, it's a long time since I came across this name. Then, very soon, in 1864, John Newlands, who was an English chemist, physicist also, he proposed the law of octaves. I'm giving you only the timeline now. After this, I'm going to go back to each one of them in more detail. So, repeat: 1649, discovery of phosphorus; 1829, Dobryner, his halogen and alkali metal triad; 1862, Deschancourt, right? Deschancourt. His name is Deschancourt. Now I get it back. Deschancourt. He gave us the classification of elements in order based on the periodicity of chemical and physical properties. Then came 1864, John Newlands. He gave us the law of octaves. Then the so-called really proper kind of a periodic classification was dreamt by Dmitry Mendeleev. Mendeleev is supposed to have dreamt his periodic table. Imagine. We'll see a lot more to be told about him. We will take up. He gave us the first periodic table based on atomic masses. Again, we will come back to him later point. Then 1870, Lothar Meyer, he gave us one periodic table of his own. Then 1895, Lord Rayleigh discovered argon, which is an inert gas. Till then, inert gases were not known to people. Then 1898, William Ramsay helped to establish this so-called zero group of elements, and he predicted the future discovery of neon. Incidentally, that brings one more issue to mind, one more point to mind. William Ramsay was one of the scientists who founded, or who was the first of the scientists who started our very prestigious Indian Institute of Science in Bengaluru. Indian Institute of Science in Bengaluru, which is a world-class research center. All of us, some of you have seen it probably, some of you have heard about it, and all of you have definitely heard about it. And I was one of the very, very fortunate people who had a very brief association with that institution for some time. I used to go there for my reference work during my doctoral work, and this is all about 30 more years ago. Then I did some measurements in the laboratories. It is a pristine place. Well, it's fantastic. How I wish one of you or a few of you can enter the annals of that great institution. Then in 1911, Ernest Rutherford established that nuclear charge on the nucleus is proportional to the atomic mass of the element. This was a turning point in the discovery of in the framing of periodic table. Then 1911 itself, Van de Broek, he established that atomic weight is approximately equal to the charge on the atom. This charge became later on came to be called as atomic number, by which today's modern periodic table is based upon. Then 1913, again a turning point. Henry Moseley discovered the isotopes of elements. This discovery established that properties of elements vary periodically with their atomic numbers and atomic masses. And 1940, Glenn Seaborg discovered plutonium and the transuranium elements from 94 to 102. Oh, this is a very lengthy timeline. I repeat the timeline for those of you who have missed a few points here and there. One by one, retrace. I would begin always with Canada, but here's the past history. It's not mentioned in the textbook, so I don't want to risk that, but you should know it, feel proud about it. 1649, phosphorus. 1829, Dobryna. 1862, cylindrical periodic table, Deschamps Courtois. Then 1864, Newland's Law of Octaves. 1869, Newland's Law of Octaves. 1864, I'm sorry, 64 was Newland's. 1869, Mendeleev, first periodic table. 1870, Lothar Meyer, he did a work on atomic volumes. He gave a periodic table to us. 1895, Lord Rayleigh discovered argon, the first of the inert gases that came to be known. Then 1898, William Ramsay, whom I talked just now. He helped the establishment of the zero group of periodic table, and also predicted the future discoveries of neon and other gases. 1911, Ernest Rutherford, he established that nuclear charge is proportional to the atomic mass. 1911, A. van den Broek. These names are a bit strange to us because we're not familiar with those. They could be Swedish or German names. I think this is a van den Broek, looks like more of a German name. Then he established that atomic weight is approximately equal to the charge on the atom, and we know the charge on the atom is nothing but your atomic number. So this also gave us a classification mode to classify elements on the atomic numbers. Then 1913, Henry Moseley, he discovered isotopes, a very important discovery for us. This established the properties of elements are vary periodically with atomic number and not atomic mass, as was predicted by our Mendeleev. And in 1940, very recent origin, just about a century ago, about 100 years, not even 100 years ago, 80 years ago, John Glenn Seberg, he discovered plutonium, and then they saw transuranium elements, all of which we're going to see later. So all this is very interesting study. In fact, this study becomes important, and as I've always been mentioning to you, to know something, we should be made to get curious. We should be only then we begin to learn. See, it is like one statement that I follow. It says the hungry baby gets milk. So if the baby doesn't get, crying baby, not hungry, I'm sorry, the crying baby gets the milk. If the baby doesn't cry, a small baby, a 2-3 month old infant or 1 month old infant or a 10-day old infant, if it doesn't cry, the mother will not feed it. Although the mother feels instinctively that this child needs, she'll wait for this child to cry. So the crying baby gets the milk. Exactly like that, the student who wants to learn will get knowledge, will get information. Information will not just come to you like that, it will not be poured. This has been happening all these years, but now things are changing. Now it is going to be based more on your experiences, your experimental techniques, and so on and so forth. Well, all this is, again, as I said, this is a prologue to what we are talking today. All right. So Dobriner, the first so-called official classification was made by Dobriner. He tried to arrange elements with similar properties into groups. He identified that some groups having 3 elements came followed a particular pattern, and these 3 element groups were called triads. He found that when 3 elements were written in the increasing order of their atomic masses, the atomic mass of the middle element was approximately the average of the mean of the atomic masses of the 2 terminal elements. What do I mean by this? Let us see. I'll write down one triad for you. Let us see if it makes any sense to you. I'll write nitrogen, phosphorus, arsenic. No, that will not make sense to you because that will put you off from what we're learning. I'd write calcium, then I write strontium, and then I write barium. 3 elements I'm taking here to begin with. atomic mass of calcium is about 40.1 to be more precise. Then that of strontium is, let us keep strontium there. That of barium is 137.3. By Dobrina's calculations, the atomic mass of strontium should be the average of these two. Let us see what we get here. Let me add 137.3 to 40.1. I would get 771. Divide this by 2, 88.7. I get a value of around 88.7. Actually, the atomic mass of strontium happens to be 87.6, very close to what was predicted. I'll take one more triad for you. I would take chlorine, bromine, iodine. You can calculate. Chlorine is 35.5. Bromine, we will keep it. Iodine is 126.9. You can calculate and see what will be the value that you get. You will get a value of around 81.2, but the actual value is 79.9. Now we find that the atomic mass of the middle element is approximately the average of the atomic masses of the two terminal elements. But this was not a very successful experiment because when you look at a triad that he had proposed of nitrogen, phosphorus, arsenic, he found that atomic mass of nitrogen is 14, atomic mass of arsenic is 74.9. So our value should have been 44.45, but we are getting a value of 31.0. So there was a large deviation from the expected atomic mass to the one that was actually found. So you find that the halogen triad and the triad of alkali earth metals was quite consistent with what the Dobrina's triad was talking about, but it did not meet the requirements for other elements also. So this had to be kind of disbanded. In that sense, it had to be shelved because people said, oh, well, this man is talking through his head. But anyway, with due respects to what he said, we'll have to understand the ingenuity, the genius of the man. He had the patience. He sat through a lot of literature. He read a lot of information. Then he began to construct this periodic table. Whatever little he could do, he did. It was a landmark, statement that he made. Then came the precursor to the modern periodic table and the Mendeleev's periodic table. It was called the Lands Law of Octaves. Now, this is a very interesting thing. Now, I'll put an apostrophe after Newlands because don't read this as Newland apostrophe. Yes, there's a small correction because I'm sorry, I'm interjecting with a little bit of English too. This is the need of the hour. Many of us commit certain blatant mistakes while writing. Newlands is the name of a person, so we are not supposed to put an apostrophe here. Put the apostrophe after Newland's Law of Octaves. This is a law which is based on even what we follow, the Swara system. The Swaras, I think you're all familiar with, you must be familiar with. I mean, I don't know, I shouldn't say you are, I assume no assumptions. You must be because we are born into the land of music. The land that gave music to the world, if I can say so. we have the Saptaswaras, Sa, Re, Ga, Ma, Pa, Dha, Ni, and the eighth one again is going to be Sa. The Westerners copied the same concept. They wrote another notation, their own notation they wrote, poor fellows. Let us see what they wrote. They wrote it as Do, Re, Mi, Fa, Sa, La, Ti. Do, Re, Mi, Fa, Sa, La, Ti. This actually was our Sa, Re, Ga, Ma, Pa, Dha, Ni. Now you know that after Ni, again one more Sa will come. So what Newlands did was, he said when you arrange elements in the increasing order of their atomic masses, mind you, till then atomic masses or atomic weights was the only known concept to people. They never knew about the atomic number concept. There was no mention of protons, neutrons, etc. We are still talking about the Daltonian era, when atom was supposed to be indivisible, etc., etc., and people had vague ideas about the atom itself. So he said, you arrange elements in the increasing order of their atomic weights. I'll use the word weights. Then you will find that elements having similar properties will fall one below the other. Let us see if it works. Let us write, let me leave out hydrogen, helium, because there are two extremes. I mean, there are two separate entities. We'll not talk about them because helium was not even known by then. Only hydrogen was known. So leaving hydrogen out, we start with elements like this, sodium. I put this table, make it a proper table for you to the extent I can. I write sodium, then lithium, then beryllium, boron, carbon, nitrogen, oxygen, fluorine. So it should have been, I think it should be hydrogen. If I complete this, put a question mark here. Then chlorine, bromine. And before chlorine and bromine, one more thing, cobalt and nickel. And then bromine. So he brings the sodium, below that potassium, below that copper, below that rubidium, then beryllium, and then magnesium, then calcium, zinc, and strontium, boron, aluminium, chromium, yttrium, cerium, and lanthanum. Cerium and lanthanum. Then carbon, silicon, titanium, indium, and then zirconium. Then nitrogen, he wrote phosphorus, manganese, then arsenic. This was not known. Oxygen, below that sulfur, iron, and selenium. Well, this is what Newlands wrote, or not what I'm writing. It is all what information Newland gave us. All right. So you can just peruse this for a moment. Keep perusing this. And we will find out where our mistakes, where were the mistakes that were there in this periodic table. Okay. Now, I'll just add on one more information. I'm sure that it is coming up just now. I'm waiting for that to happen. It's coming on my screen. Okay. Yeah, it was not sodium, it was hydrogen. It was a, that is where I got a doubt. I put a question mark here. It was coming up as hydrogen. Well, when you look at this periodic table, you find that many things are what they should be. For example, fluorine, chlorine, bromine, they are together in the modern periodic table. Lithium, sodium, potassium, rubidium are also together. Beryllium, magnesium, calcium, strontium are also there. Boron, aluminium together. Chromium doesn't, yttrium doesn't. Cerium, lanthanum, leave them. Carbon, silicon, yes. Nitrogen, phosphorus, yes. Arsenic, yes. Oxygen, sulfur, right. Selenium, okay. But iron is out of place. So let me take out the ones that are not in place. I use a different color if possible. I'll encircle this. I'll encircle this. I'll encircle zinc. I'll encircle cerium and lanthanum. They're special elements in a way. Then carbon, silicon, titanium, let it be. Now, manganese doesn't come there. Iron doesn't come there. So these are some oddities that were found in the periodic table given by Newland. So when you apply Newland's law of octaves, it is applicable for the first elements, a few elements, only up to calcium, because after calcium, what happens? Every eighth element does not resemble in its properties the one previous to that. So every eighth element does not follow the properties of the first. Then Newland's, okay, this is one more interesting point. When Newland's framed his periodic table, that period of time, we go back to that history of that. Newlands was in 1864. Then only 56 elements had been known to mankind. Today we have 118 elements. Only 56 elements were known, and Newlands assumed that there will be no further discovery. This is the end of the world. He said, yes, like our people on during every eclipse, we find people talking on the television. Any local channel, vernacular channel, you switch on, you find the so-called what do you call them? Call them anything. They come out with predictions saying that this is going to happen, that will happen. So everybody had predictions of their own. Newlands had his own prediction. He said that the 56th element is the last. Beyond that, nothing exists. There will be no further element to be discovered. So what I have said is idam itham, the truth, the absolute truth. But later, just after a few years, a large number of elements came to be discovered. So his law was a flop or a failure. I wouldn't call it as a flop, it was a failure. Then in order to fit elements into his table, it is like, trying to make a frame and then put a picture into this. Usually what we do is we make a picture and then put a frame, but this man had made a frame and tried to put a picture into this. So in the process, what he did, he started putting elements in the same slot, two elements in the same slot, cerium and lanthanum, cobalt and nickel. He started putting them together, grouping them together, clubbing them together. And also, unlike elements began to fall one below the other. So this cannot be accepted, because you cannot make a statement saying this is it and gone. This you have to follow what I said. It just cannot happen. People didn't want to believe that. So his theory fell through. Like cobalt and nickel, they're placed with halogens. They're no way related to halogens. Hydrogen, yes, to some extent it has a property like halogen. It is univalent. It is to an extent a non-metal. We'll be talking about hydrogen itself on a special occasion. This is one element whose position even today is not fixed. So many years have gone by, but still now, even now, as on date, the date being 6th of November 2020, the position of hydrogen still is elusive. So leaving that, fluorine, chlorine, bromine definitely are halogens. They should be together, but okay, hydrogen granted, but cobalt, nickel do not come in that place. And similarly, lithium, sodium, potassium, rubidium, they are together. Copper does not fit into that group. Zinc does not match with beryllium, magnesium, calcium, so and so on and so forth. So this gave people something to think about. They said, well, we will have to see how we need to make a new periodic classification. And in comes our great Dmitry Mendeleev. Mendeleev's story, I think you have read about Dmitry Mendeleev's story. I think if you have not read, please go through his biography. It is available on the internet. You can just Google his life story, a small biography you can go through. And if you are more interested, you can do a little more study on that. He was born into a very good family, but of course something went wrong in between and he became a destitute. He had no finances. He worked in different places. He went through a lot of hardship. Then he began to work in different places, and ultimately he sat in a laboratory and started to work. Now, please go back to that period, 1869, if I remember the date was. It was, yes, 1869. The world was very, very divided. It's not like today is we call ourselves as global villagers. Sitting here, I can talk to anybody in any part of the world via a live video call. Today, I can hold virtual meetings with anyone, anywhere in the world, whichever part of the world he or she be. But we're talking about that period of time when everything was isolated. Russia was isolated, USSR was isolated from the rest of the world. He had to sit and collect information from different sources. We don't know how he managed. And assiduously, painstakingly, he started to write for every element that was known. He started to compile its oxides, its chlorides, its nitrates. He began to calculate their atomic masses, molecular masses. Then, after all this, he said, here is some kind of a format. This format is going to give me an idea about what periodicity is all about. Now, at this point, just we'll take a small breather for a minute. Let us imagine. Why should we imagine? We do it. We go to a library. Let us say we go to a school library. You want a particular book on optics. Now, there are two choices in front of you. One is find out where optics books are placed, that is, where physics books are placed, or go to every bookshelf and try to locate what you want to. The second one is a very, very laborious process. It is something like what I do when I go to a supermarket. If I want to buy something, because I don't ask people, maybe that is my weakness. I don't ask people. I assume that I know. There's a problem with me. It's okay. So I just go to every shelf. I love going through every shelf. That's primarily the objective. I love going to all the shelves, looking at whatever the contents are there. Finally, when I go 2 rounds, the shop assistant will come to me and ask, Uncle, what do you want? Then I'll tell him, look, I'm looking for this. Array, it is there only. Why did you take the trouble of going around? Then I'll say, I'm so sorry. I didn't note, etc., etc., notice, etc. So you will have 2 choices. One is going to the particular section, going to a physics section, looking for books under electronics, optics, sound, and so on. Then locating that particular book, which is much more easier than going through the whole stacks of books that are there in the library. This was the situation when Mendeleev started his work. He had a lot of information. He did not have access. He had access to a lot of information, but nothing was properly scientifically arranged. Then he thought and said, okay, let me see how I can do it. He started to slowly arrange elements in the increasing order of their atomic weights. Because by then definitely people had come to understand the concept of atomic weights. So he knew a lot of information, and I'll just give you a small information about Mendeleev. I just go and got it out now. It was on the other system. He was born in Siberia. He had his early education there. Then he went to university just because his mother wanted him to do so. We had great mothers even then. She instructed with example, corrected with love, and traveled with him to places, spending her last resources and strength. And of course, later on, he writes a lot about her. And he dedicated his entire work to his mother. So, those of you who are watching, please remember this is a kind of a tribute that every mother, no mother wants it, but will definitely deserve it. You have to give such accolades to that great woman who has brought you into this world. All right. So Mendeleev, when he started to do his work, only some 63 elements were known as compared to 118 today. There are only 63 elements that were known, and it was like finding a needle in a haystack. And he slowly examined the relationship between atomic masses and the physical and chemical properties of different elements. And he started to arrive at a particular sequential form. Now, the greatness of Mendeleev has to be emphasized here. He was able to predict the next few elements that were not known to people. There were elements that were unknown to people, and he could predict them, not only the element's atomic mass, its position, its oxide, its formula, its molecular mass, its melting point, its boiling point, the halide, the nitrate, every one of them very painstakingly he sat through. And this is what we call as work of a genius. He spent his whole lifetime doing this kind of collating work. And then when actually the elements were discovered, we found that they found that there was a very striking similarity between what he predicted and what was actually found. Then he was the man who gave us the first concept of periodicity. He arranged elements in the form of a table. So he called this as the periodic table. Before we go into his periodic table, let us look at his law. It says that properties of elements are periodic functions of their atomic masses. I repeat, properties of elements are periodic functions of their atomic weights, if I can use that word of his own terminology during that period. Properties of elements or periodic functions of their atomic weights. So he wrote a table which had two formats. Left to right, he called this as a period, and top to bottom, they were called as groups. So in the periodic table, vertical columns are called groups, horizontal lines are called periods. So when I say period, it means it is repetitive. Like you have in your timetable a period of 45 minutes, sometimes a period of 1 hour, depending on the convenience, usually 45 minutes. So we have a pattern. Monday morning, first period, second period, third period, fourth period, fifth, sixth, seventh, eighth, whatever the number of periods we have. Tuesday, Wednesday, like this, we have a periodicity. Here also, he came out with this concept of periodicity. He made the elements classify into periods and groups, and he wrote his periodic table, which is there in your textbook. I want to take your attention to page number 83. If you have your book with you, just open page number 83. You have his periodic table that is given to you. if you look at the top, you find the oxide being given RO, its hydride being given RH, first group, second group RO, RH2 is its hydride, third group oxide is R2O3, R is an element, then for example Al2O3, B2O3, SC2O3, etc. Then its hydride RH3, for example, borane BH3, or yes, you can say aluminum hydride ALH3. Then fourth group, he called it as RO2, it's oxide. RH4, it's its hydride. For example, carbon oxide CO2, carbon's hydride CH4, and then silicon SiO2, SiCl4, silicon tetrachloride, and so on. Then he came out with the fifth group R2O3, where, or R2O5, he gave us both R2O3 and RH3, R2O5 and RH3. R2O5 for nitrogen pentoxide N2O5, phosphorus pentoxide P2O5, and hydride ammonia NH3, phosphine BH3, and arsine ASH3, arsenic oxide AS2O3. Then he split the next group into the so-called sixth group into A and B. Of course, both of them are having, all of them are having group A, group B, A and B separately. Sixth group, he had oxygen, sulfur, selenium, tellurium coming under one part, and chromium and molybdenum and tungsten coming in one more part. Their oxides were given, hydrides were given, like this. He gave us a number of classifications of elements. Not, as I said earlier, not only did he talk about the element, he talked about its oxide, its hydride, its melting point, its boiling point, and so on and so forth. Now, there were some challenges that he had to face, like when he started to arrange elements in the increasing order of atomic weights. He found that there were some inverted pairs. He could not account for it. For example, if you look at potassium and argon, if I remember those two names, argon and potassium, argon comes before potassium. Atomic mass of potassium is less than the atomic mass of argon. Similarly, cobalt is followed by nickel, where cobalt has atomic mass of 58.93, nickel has atomic mass of 58.71. So by his logic, nickel should have come first and then cobalt should have come later after that. But that would not fit into the elements above them, because cobalt comes, iron, cobalt, rhodium, they come together. Then nickel, platinum, palladium, they come together. So if you inverted this, then there would be a problem, but he was not able to account for it. But his achievement was he could predict the presence of an element called gallium. He did not know the name gallium. He called it as similar to aluminium, and it was called eka aluminium. Eka means a similar to. So eka, it is eka. Eka, is in Sanskrita, eka is one. So he had taken that and he prefixed the name by eka aluminium. That means it is similar to aluminium, one above or one below aluminium, one preceding element. Then scandium, gallium, germanium, they were all discovered by this, thinking. Well, Mendeleev had successfully given us a periodic table, but as I said, there were some challenges. One was the presence of the so-called inverted pairs. The other, of course, has been their position of hydrogen. The third one was there was no place for inert gases, because when inert gases were discovered, the rare gases, noble gases as we call them, when they were discovered, they did not have a place to be occupying in the periodic table. So these were main challenges that Mendeleev had to face. Then he also put halogens along with alkali metals. uh, like he said, just like NaCl, there should be HCl. Like Na2O, there is H2O. There is, just like Na2S, there is H2S. So hydrogen and alkali metals are going to be together, you know. But the problem arises. As I said, HCl is covalent, NaCl is totally ionic electrovalent. And H2O we know is covalent. H2S is also covalent, but it is a gas. This is a liquid, although it has higher molecular mass. And so is the case of your oxide. Sodium oxide is very strongly alkaline. Water is neutral. So there are a lot of small restrictions that this table had to face, and this gave us it gave birth to the new or the current so-called modern periodic table. Now, going to the history of the modern periodic table, when neutron was discovered way back in 1940. Till then, the structure of the atom, you all gone through the structure of the atom, you know very well that there is a nucleus, and around the nucleus there are electrons and shells, and their number of electrons is always equal to number of protons, and protons are held together by neutrons. All of us know this basic information. Well, we also know the concept of atomic number and mass number. Mass number being the number of protons and neutrons together, atomic number being number of protons or number of electrons. Well, when all this is happening, Mosley started to work on cathodes of different X-ray diffraction patterns of different cathodes. He took a metal piece, hit it with X-rays, and there is a property, there is a phenomenon in physics called diffraction, that is bending of the light or the ray. And he started to study the diffraction patterns of different cathodes, and he found that the pattern was somewhere related to the nucleus of the atom. And in the nucleus of the atom, he said what really matters is the number of protons. So he made the statement that the atomic number is a more relevant to giving the periodic table, framing the periodic table, rather than the mass number. So on his calculations, based on his work, the periodic table had to be redesigned, and then came our so-called modern periodic table. The modern periodic table we know consists of, as given by Mendeleev, we have the periods and we have groups, but there is a difference. Well, periodic table given by Mendeleev had subgroup A and B. Here we don't have any such subgroup A and B. Of course, even this version was preceded by one more version that was there when we were students long ago, but that we are now following is the long form. So the long form of the periodic table has got 7 groups and 7 periods and 18 groups. So 18 groups of the periodic table are there, and we will be looking into these 18 groups and the properties of certain elements, certain groups and periods when we meet again in the next week. So thank you very much for being patient. Today we are finishing the class probably about 2-3 minutes earlier with a reason that if there are any queries here, if you have posted them on the chat box, I'd like to take them right now. Thank you.
Thank you so much, sir.
Any
it
questions?
was nice session. No, sir, we didn't receive.
Okay, dear. Thank you very much, friends. So in that case, we meet again on the following Friday with, I think we might be able to finish more or less 80% of what is remaining, and then we will plan what is to be done next. Thank you very much. As usual, do like what we are doing, and in case you have any reservations, please mention them in your chat boxes. Thank you very much. Have a great day, great week ahead. Thank you. Bye.
Thank you, sir.
Thank you, dear.
Dear viewers, stay connected for many more sessions. Please like and share the video. Thank you.